hear me well? Is it clear? Is the microphone working? Okay, thank you. So, good evening. It's great to be here. This is my first time in Aspen, and I want to thank the organizers of this series that have invited me to give this lecture. It's an honor to be in front of this community who cares so deeply about science, and certainly I have big shoes to fill looking at who are the previous speakers in this series. So my plan for today is that we will take a journey into the microscopic world. We will go beyond the molecules, beyond the atoms. We will enter the nuclei of the atoms. We will focus on a tiny, tiny particle called the proton and its partner neutron. And just to understand how small this proton is, let's compare it with something we know how well the size it is. Take a grain of salt, table salt, the tiny one. So if I want to take protons to occupy the same space as a tiny grain of salt, I would need 200 to 300 billions protons in a row. So you see how tiny this is. And this means that we have to have special techniques to study it, and I will talk all about this today. While preparing for this talk, one question was coming to mind, and that question was asked by a high school student in Central High School in Philadelphia. I was visiting to give a talk on nuclear physics and why it's important to study STEM and so on. One student reluctantly asked a question, which is, if the protons are so tiny, why do you need such huge supercomputers, right? Leave it to the kids to ask the right question. So, by the end of this lecture, you'll have an answer that you can then go and brag about to your friends and family. Okay, so you heard a lot about me. I would like to know you a bit more. So please take your phone out. This is a phrase I don't use frequently, especially not in my lectures. Scan this QR code. It will take you into to answer one question. And the question is, what is your profession, field of expertise? It gives you more than one options, and we can see the results live. Give me a moment. I can show it here. This is the same QR code. So we have high school student, intern. That's great. So this talk is right for you. So we have a cut. Article physics. So it's a great group of diverse audience that it helps me adjust my pace and also the jargon I will be using. Okay, that is perfect. Thank you. You can keep adding your answers if you want. I will look at it after the presentation. I'm a theorist. And theorists love their equations. We put them in coffee mugs, we put them in t-shirts, people tattoo them on their bodies. So it's very hard to give a talk by eliminating all equations, especially when it is to such a complex topic like understanding the proton. So for those who are not experts, if you see this sign on the slide, it's just to tell you, do not bother yourself with the slide, just listen to what I am saying. I will explain things in a simple way. Often in science, we address this golden circle question of what, how, and why. And while it differs from field to field, kind of the questions are the same. what are we addressing, how can we solve it, and why does it matter. And in this particular case, I will talk about the proton, which is the building block of the visible matter. We use experiments and theories and numerical simulations with supercomputers. And of course, from the science perspective, we want to understand the subatomic world, but there are reasons for the society to care about, and I will talk about this in a moment. Mentioning a visible universe, it would be an omission if I didn't say that this is only a tiny, tiny part of what is around us. So ordinary matter is 5% what's around us. This is basically everything on Earth, the galaxies, the sun, the gas, the stars, and so on. Everything classifies under this. And if I were to give you an artistic impression of what we know, we are somewhere here that we think we know what is going on. We actually know very little, but there is a lot of areas to explore, and this is beyond my field of expertise, and maybe the next week's talk will address some of these topics. I will focus on the ordinary matter, and this is governed by 4 fundamental forces that make the world we live in as we know it. So it's gravity, electromagnetism, weak interaction that is related to decays, and it drives the fusion change in the sun. But the highlight for today's presentation is the strong force that is responsible to hold the protons together. That's why we exist and we don't annihilate. We are made out of stable particles. And when it comes to the proton and other fundamental particles, a strong interaction is responsible for that. However, this is not the whole story. You don't have to go into the microscopic world to be able to see the implications of the strong force in the proton, but it has played an important role from the evolution, in the evolution of the universe from the Big Bang to the present time and beyond. And in fact, if you take a close look at this evolution chart, you will see that 10 to the minus 6 seconds, which is almost instantaneous after the Big Bang, we have the formation of the proton and the other fundamental particles. So they have been playing an important role in how this universe, the visible universe, was formed. Okay, so I did mention that this is a tiny component. I want to reiterate that the proton is inside in the nucleus of the atom. You have protons and neutrons, and I will focus on this particular one here. And I want you to take a look at this figure, at this plot here that basically shows these 3 circles. These are some 3 balls. These are special kind of particles. We call them valence quarks. So, and these give the characteristics to the proton. So, how do we know it is a proton? We always see this composition of what we call quarks, an up and down classification of quarks. And however, we know that because they're at the core of the visible matter, if you look at the theory, you will see that more than 99% of the mass of the visible matter is made out from these particles, protons, neutrons, pions, kaons, and other particles existing in nature. And you should always remember that finding these 3 quarks means you have a proton. But these 3 quarks don't exist in vacuum. There is no vacuum at that level. We have what we call a restless quantum sea. It's a sea of quarks and anti-quarks and gluons that are like springs holding the protons to the quarks together. I tell my undergrad students that they have to always think as the QCD vacuum. The vacuum in this area being a pot of boiling water, where you have these bubbles created and so on. So it's a very unpredictable behavior. Okay, so we want to study the proton. We know it has implications in nature. How do we study? We can do experiments, but in order to be able to do all of these things, you need support by theory. You need to develop a theory that describes the phenomena that you're interested in. And scientists agree that this is the theory of quantum chromodynamics. I will refer to it as QCD for short. And we know that QCD has all the nice properties that produce the phenomena caused by the strong force. Some people call it annoyingly agreement with what we observe in nature, this particular theory. And what you need to remember is everything that we study within the strong force is through the quarks and gluons. So these quarks are almost massless particles that exist inside the protons. Gluons are massless. They're like springs that they attach to their ends quarks, and they interact with each other, but also springs know the existence of other springs. So it's a mess of a sea of particles inside the proton. Now, QCD is a relatively young theory. It's about 50-ish years old. And I was looking outside the poster, and I realized that if somebody was giving in the 60s public lecture, QCD didn't exist yet. So I will not be able to give this lecture 50 years ago. And for those who know a bit more about the forces, QCD is incorporated into the standard model of particle physics. It's a wonderful theory that describes the many properties of strong force. And because strong force is peculiar, QCD needs to have two personalities. The quarks and gluons behave differently when they are confined in a small space, or you allow them a big space to exist. And you can see this in this figure, in this animation here. That you see some balls. These are the quarks. These tubes between them are gluon fields that are responsible to transmit the strong force between them. That's why the quarks don't just take off. They are confined by the interaction through the gluons. And one way to simplistically think about this is not a direct analogy. This has to be clear. It's a simplistic way to think about it and to explain this. Think about a rubber band, and at the end you attach two marble balls. And if you let it rest, there is no tension in the rubber, and the balls don't feel any tension. But the more you try and pull them apart, what happens is that the tension is being built, and eventually, if the marbles were quarks and the rubber band was gluons, we will have the formation of a new set of rubber band and two new marbles. That's how the microscopic world exists. Quarks and gluons do not exist free in space. They are always confined into particles like the proton. So that makes it very difficult to study because I cannot break the proton apart and understand it piece by piece. And the two personalities of QCD is exactly this effect. Small distances, the quarks feel as if they were free. Large distances, they just feel the tension to come back together. And because this is a very complicated theory, we need large-scale numerical simulations done on supercomputers. We'll come back to that. This property of QCD, of asymptotic freedom and confinement, has been awarded at the 2004 Nobel Prize. So this is a big deal for the community. It validates that the theory reproduces what we see in nature. And as I said, we recently celebrated 50 years of QCD. And a group of scientists, we came together and wrote this article, which is intended for graduate students level. So you can find it in libraries in your institutions if you're interested to learn more about this. Okay, so we have seen a peculiar behavior of QCD, or the strong force, I should say. And another example is the mass generation. we usually we refer to it as weight in our everyday life. So let's take an example that we can all resonate with. I have two apples. I put them on a scale. I see what the scale reads. Then I take a basket. I do the same thing. I take my calculator and I add the two numbers, and I know what what would be the value on the scale if I had weighted the apples inside the basket, right? This is, you don't have to do everything separately. You put everything in a bowl and then you weigh it all together. All right, let's see another example of mass generation. Now this is related to the electromagnetic force that is responsible to hold together a hydrogen atom that is made out of an electron and a proton. And don't look at the numbers. We don't report masses in kilograms, in pounds. These are tiny, tiny objects. We have a different system to indicate them. So don't worry about the numbers and what it says MeV over there. But the point is that if I add the masses of the ingredients and I subtract a very small number, which is what we call binding energy, because nature likes to release energy when it creates favorable states, like the hydrogen. Otherwise, there is no incentive for an electron and a proton to bind together if it weren't to be a more stable state. But we understand electricity and magnetism. We understand this theory because we have a full control of how the mass is made. So let's see how the strong force would behave. I am taking the proton. We talked about these three fundamental quarks inside the proton that make the mass of it. So if I do the same exercise, which is very simplistic, I should say, we find the value of 9 MeV versus the value of the proton being almost 1,000 MeV. So it's 1%, these three important quarks, that whenever they come together, we have a proton. They are not responsible for the proton. And now we know. So basically what I am saying here is that you have the visible matter made 99% by particles like the proton. It's the mass of the visible matter comes from the mass of the proton, but the proton itself is made out of massless particles or almost massless particles. So we understand this now. It's peculiar, but we understand it because the mass generation in the level of the strong force is made out of the energy of the quarks and the interaction with the gluons. So this effect is extremely important, and it translates into the mass of the particles. Okay, you might be wondering, is this real? Can this be the case? Maybe you're making a mistake. Well, I will refer to nature to answer this question. The question is, why can't I study the quarks themselves and understand the properties of the proton? Well, let me give you an example from nature. Let's take this starling. You have this bird, you can study it, you can see its eating habits, how it likes to behave in its environment. Always you work with a single starling, and whatever you learn about the starling, it will never ever explain this phenomenon you might have seen in nature. This is the murmuration of starlings, and you see that it is the interaction between the different elements that creates something that cannot explain on an individual basis. And there are also schools of fish that behave the same way. So this is mesmerizing, I dare to say. Okay, so the strong force, we know it leads to complex phenomena. So how can we study them? So I mentioned that we developed a theory, but what do we do with this theory? Spoiler alert, pen and paper calculations do not work. It is very complex. You tell me, how can I describe a pot of boiling water where I throw pasta inside and I observe the behavior of the pasta and the motion of the pasta? Can we do it? We cannot do it. Every time You repeat the experiment, you take a different pasta, you get something different. That's how the QCD vacuum behaves. This sea of particles of quarks and gluons are so complex that you cannot solve it analytically. And experimentalists who have some colleagues here, they use high energy collision experiments. So they collide beams of particles, they see what comes out of these, they have detectors that can then reconstruct and see what is inside the particles at hand. But I'm not an experimentalist. There are theorists who will do very elaborate calculations. They can use some computational tools, but it's kind of a pen and paper. But there are limitations to that. You can get up to a certain level. And this is where my research comes, which is numerical simulations. And I will show you how we can do this systematically through using supercomputers. I should say that each one of these methods will give you very nice results and results that stand alone. However, what the community works in is to have synergistic activities. So we bring together our expertise. Experiment can do well one thing, theory can do well something else, and can guide the experiments, and numerical simulations can have predictions. So all of us collectively can get the best outcome we can. And these numerical simulations, I like to, this idea of having numerical simulations, it's not, I like to believe it's not unique in nature. And I use my Greek heritage to give this example. This is Alexander the Great. It's a painting of Alexander the Great. He's doing something that I will explain. And this basically took place in 333 BC. There was a prophecy that said there is in Gordian, there is this, in Gordon, there is this very famous knot. It was very complex. You can see it here. And the prophecy said that whoever unties the knot, it would rule Asia, all of Asia. So many people try to do this, kings and so on. Everybody failed, and therefore, and then Alexander the Great was called, and he studied a bit the knot, and then very dramatically takes out his sword and cuts the knot. And this is what you see here. And he says, "Oti de linete kovete," and this is Greek for cut whatever you cannot untie. And I like to say, have a beautiful theory, but it's very complex. It looks nice on a mug, but if I want to do calculations, I cannot do them with a pen and paper. So I like to brag that, well, simulate whatever you cannot solve analytically. And the message is that humanity was always trying to solve complex problems, and sometimes we have to be bold and take a new approach to things. And numerical simulations is one of these. Try and understand the strong force and beyond. Okay, here is now a technical slide. So basically, how do we do the numerical simulations? We have finite computers. We basically discretize space-time. So instead of living in a continuous space-time, we just create pixels. Like you see, oops, oh, spoiler alert, no. Okay, never mind. You see, I get very energetic and enthusiastic when I talk about this. So this is our lattice. We call this lattice QCD. So if I don't say numerical simulations and say lattice QCD, that's exactly what I mean. We discretize space-time, and Kenneth Wilson, who got the Nobel Prize in 1982, he has proven that this works very well. We don't lose physical information. We can reconstruct nature, but I'm not going to go into this. And this pixelization has a very important effect. So I am giving you this picture. I took it with a very bad camera. You don't know what it is. Well, now you know what it is, but you don't see what this is. And then we take a better focused camera and I see something formed, and then I need to have state-of-the-art lenses to be able to see the clear picture. In a similar way, this is what we need to do on the lattice. When we create these pixels, we don't want the pixels to be very large. We want them to be closer and closer to each other so we can get a good picture of the proton. And the cost of that is that becomes extremely expensive. And I will tell you how expensive that is in a moment. This is a very interesting plot here, just to show that with red, so basically this is a calculation done, the same calculation done over the years with different computers. You can imagine in 1978 what kind of computers they had and what kind we have now. But you see the cost of the computation went from more than 300 years to a few days, basically, by utilizing algorithms. And we're now in the exascale era where we have the first computer at Argonne National Lab called Aurora. And I should say that access to this computer is not given, is not gifted to scientists. We have to write proposals and be peer reviewed, compete with each other, and funding agencies and panels decide who can get funded. Okay, so moving on, I want to be clear that lattice QCD, these numerical simulations, don't exist in a corner outside experiments and other theories. But you see here that different investigations that we do, including the proton, but also astrophysics, it's related to many, many different facilities worldwide. This is just an example. This is not a complete list. And the community is very excited about some new developments. This is the Electron-Ion Collider that will be built in the US at Brookhaven National Lab in Long Island. And this will be one-of-a-kind machine that will smash electrons into protons and nuclei, will have power detectors, and will allow us to reconstruct what happens during those collisions to give us an understanding of the proton. I should say here that you might be wondering, well, can you take a microscope and look inside? We go back to the size of the proton. The most sensitive microscope we have, they're still at a scale which is tens of thousands more larger than the proton. We cannot use a micro. That's our tool experimentally. We need to smash particles and see what comes out of it. I'm not an experimentalist. I'm not going to dare to go there and explain more. But what I want to say is that this is a big deal for the community. It has all come together to understand, to support the EIC. Even though it's being built in the US, it has international support. All the scientists worldwide are contributing. And we are here for a program this month that started this week, which is on EIC science. It's supported by National Science Academy. So it's a big deal. What I want to focus on are on two questions that have identified as critical for the EIC to answer. One is the mass of the proton, and the other one is the spin of the proton. Now, these are the two topics I will spend the remaining time on. So before I talk about the spin, I need to define it first for those who are not familiar. This is a property that particles like the proton have, and it is as fundamental as their mass is, as their electric charges, and so on. It's an intrinsic form of angular momentum. This is not a twirl. They're not spinning around, but it's convenient for scientists to call it a spin. It does determine the behavior of the matter as we know it, and you can think about it as a quantum property that makes particles act like tiny magnets. They're very strange, but absolutely essential. And scientists have been studying the spin for scientific curiosity, but controlling the spin has led to new technologies. Whether it is from hospital machines like the MRI, nuclear magnetic resonance used in chemistry, magnetic memory cards, quantum computing nowadays, and ultra-sensitive sensors, controlling and understanding the behavior of the spin, they have been transformed into society for everyone to enjoy. So that's extremely important. I mentioned the word puzzle here. That's because in the past we couldn't understand how the proton, what gives the spin to the particle. I come back to this picture where you see the three quarks, and since the macroscopic characteristics of the proton comes from these quarks, it was anticipated that the spin of the proton is carried by these three quarks. And in 1988, there was an experiment that was conducted, and many papers were written. After that, even journalists have picked up the news and wrote sensational articles. And you see here one which is, where is the proton spin? Because when they did these experiments, they realized that an amazingly small fraction of the proton comes from these three quarks. And that was peculiar. This word is being repeated all the time here. Now we understand more QCD and the strong force. We understand we cannot ignore this restless background, this restless sea of quarks. We have to incorporate the spin contributions to those. And for the experts in the fields, I'm only saying that numerical simulations have a very well-defined method to access and simulate information on the spin. I'm happy to talk to physicists at a different time about this. But I want to show some results by starting from this point, which is pictorial representations of calculating, simulating the contributions from these quarks, both the C quarks here, and also the gluons. These are the contributions, and they need massive computational resources, and I will come back to that in a moment. Considering that we're doing numerical simulations, but we're also simulating nature, we need to reproduce physical results. This is what this plot shows here. This is a quantity, the intrinsic spin of the quarks. And what you see here with this dot is the experimental measurement, and the rest of the points are numerical simulations. The community was not always this way. It's only the last decade we are able to do all of these wonderful results. So you should not take for granted that we can just type something in the computer and it comes out of the result. So the first calculation was conducted in the late 80s. It took 3 decades to reach the point where we can actually stand proudly and say, look, we reproduce experiment. Reproducing experiment is very important for many reasons. One of the reasons is that some of these contributions are not well understood experimentally. So lattice QCD can make predictions. We can trust it since we have reproduced measurable results. And what you see here are contributions from these tiny components. And I'm not going to go into this, but I want to point out that you should take a look at how small these numbers are. So you have here contributions of the order of 1, of the order of 1/2, of the order of 1%. Can you imagine being able to do simulations of a pot of boiling water and the motion of pasta and being able to see deviations of 1%? That's what we were able to do thanks to supercomputers. Another quantity entering the spin is how much of the momentum. Momentum is a quantity related to velocity, but we prefer to talk about momentum for various reasons. How much momentum do these quarks and gluons carry? These are numbers confirming a very important point. And the point is that lattice QCD, the numerical simulations, have reached a point where we are able to talk about every single contribution, how much it gives, and in the end of the day, we get a 100%. So this gives us confidence, and the same thing for the spin. So remember the puzzle. Where is the spin coming from? This picture that was done, we have these results from 2020, I believe. We have identified all of the quarks and the gluons, how much they contribute to the spin. So experimentalists, for some of the missing pieces, can then use this as a guidance. So this is a powerful result for our community. We give more details for the experts, and it gives us a better understanding of the proton. And as I said, this is one of the 2 questions that the EIC will address. Let me touch on the second question, which is the proton mass. And if the high school student who asked me the first question was sitting here, he would again raise his hand and say, well, come on, we know the mass of the proton. We know exactly its value. Why is this a question we need to have a $1 billion facility to answer? That is because, yes, we know the mass of the proton. Is reported here in kilograms. You see how tiny it is. But we don't know what builds this, all the mechanism and all the details quantified and so on. That is a very complicated question. And as I said at the beginning, only a small fraction is coming from the mass of the quarks themselves. And this is, theorists have worked very hard to tell us how can we calculate the origin of the mass. And don't mind yourselves with the complicated jargon here. This is mostly for the experts, but what it means is that we have to add all the components. The mass of the quarks is one thing, the energy of the gluons and the energy of the quarks are other components. And this is not unique. It's basically slicing a pie, but giving physical interpretation for every single component here. So every piece you see has a physical meaning. There are more than one way to slice the pie. It has been done. But unfortunately, I don't have time to go into this. I will showcase some results that have been done from numerical simulations, but I want to highlight why this is a very difficult problem. There is this contribution here that basically is kind of missing in the sense that we are not able to calculate it on the lattice for many, many complications that are beyond our control currently. But we can assume what it is, right? So if I know the pi is 100% and I have 80% left, then the missing component is 20%. That's how we get this part here. But that's not the way we like to do things. We like to do things first principles, not rely on this kind of tricks. And that is why we need experimentalists to assist us with the EIC being able to address this phenomenon. Okay, in the final time I have, I want now to go back to the original question of the high school student, which was why tiny protons need huge supercomputers. I hope that I kind of answered it. You have seen that the calculations are far from trivial. Tiny doesn't necessarily mean simple behavior, and that's exactly what we have here. We have a very complex phenomena that the quarks and gluons are under the influence of the strong force to make up the proton and other fundamental particles. One thing that I didn't explicitly say in my talk is that, yes, we have the proton with the 3 quarks and the sea of quarks and the gluons. What happens in this theory, which doesn't happen in electricity and magnetism, is that the quarks, they interact with the the gluons interact with the gluons. In electromagnetism, we have photons. The photons are responsible to transfer the force, and photons are oblivious of each other. But if you put 2 springs together, they certainly know the presence of each other. And so that is one thing that adds to the complication. We have this very energetic sea of particles. Also, remember we pixelized space-time. So this is becoming extremely complex because we have to put on a supercomputer every pixel separately. And we have basically billions of these pixels that have to go into the supercomputer. So we need to have multiple gigantic runs. How gigantic? Our computer allocations are typically through a year. And overall, if you count all of the computer time awarded could be of the order of billion core hours. Of course, there are not billion machines. Is that just every hour you have certain number of computers working for you? If you add them together, it comes to a billion core hours. And just think what this means. If I were to do this calculation by hand, I need to take the whole population of the US and the population of Europe and ask them to do a single task simultaneously. That's how fast these computers are and how much computer power we need to be able to take into consideration all of these effects. Okay, I have come to the end of my talk, and I just want to leave you with some final thoughts that I consider maybe the most essential part of this lecture, which is, okay, this is interesting, this is nice. Now I go home and I don't have to think about this. Why should I care? And why should I, as a taxpayer, support this kind of research that doesn't seem to have immediate application in everyday life? So there are many reasons. Fundamental science is embedded into the society in multiple ways. See how what the technologies are. The discoveries we make today in fundamental science will lead the technologies of tomorrow. Also, we are trained, us and the next generation are trained in problem-solving skills, and it can be used in other sectors of the society. I believe that science elevates the society, and it also builds international collaborations. And one very important point, which is, as taxpayers, we care about our dollars go. It is only a tiny, tiny fraction of our tax dollars that go into science. And that's not to complain necessarily, but it's to say that the return to the society from this tiny, tiny investment is huge. And I can go on and explain, oh, there is this aspect you can find benefit, but I think that the best way to explain why this is important is to think about the impact it would have if we all take it away. So you would see what kind of implications would have to the society. And of course, I am speaking one-sided because I'm a nuclear theorist, but the same applies to all science of different nature. So with this, I want to thank you for coming into my talk and for giving me the opportunity to speak to you. Thank you.
Thank you, Masha, for this wonderful lecture. So now we have time for questions.
Given the fantastic progress you're making, which I couldn't have studied 50 years ago, apparently, how does our progress compare to other countries in the world?
Okay.
How's the interaction between physicists?
Thank you for allowing me to brag a bit. So, overall, the scientific community is, in my field at least, is very collegial. There are collaborations that are across different continents. So I was trained in Europe, and then US stole me, and I'm contributing here now, but I'm maintaining collaborations with Europeans. But there are certain aspects of these calculations that are very specific to the expertise of the US community. We do not like to call this a competition, but we call this typically a collaboration and a synergy. But the US is at the forefront of this. and it's because the U.S. historically has invested in taking the great people and bringing them here, and they train the U.S. society, and all of us come together.
So that trace anomaly, you're talking about the 20%.
Yes.
When you say trace, is that related to the amount or related to some matrix operation?
Okay, the question is technical. It's about the trace anomaly and why this is complicated. This is particular to the fact that QCD is a non-abelian theory. QED doesn't have this. It has a zero trace, but QCD has a non-zero trace. It comes from the energy momentum tensor of QCD, and it's highly complex for reasons I can tell you outside this lecture. Yes?
My understanding is that the gluons are constantly changing into other matter, into other particles, sometimes changing back even into gluons within this sea that is creating the energy within the proton. And although we have these supercomputers that are giving us statistical outcomes, I get that, but isn't it possible that given, at least my understanding, you know now, that the unpredictability of the changing gluon is just producing numbers that are giving us a statistical probability, but we really may not ever get to any understanding with probable certainty because of the inherent nature of the gluon decaying and becoming other matter.
Okay, so the question is very complicated to repeat, but basically, should we worry that the particles keep changing, so they will change in form? You have pairs of quarks and anti-quarks being born and annihilated, gluons and glue balls, and then we have splittings creating the strange quark, for example, and so on. Well, the numerical simulations take that into account. The theory of QCD incorporates these effects. The reason that we are doing numerical simulations is that we incorporate the theory as a whole. We just discretize. So all of these effects can be studied with the help of theories that develop appropriate operators that we can take, put them on the computer, do our calculations, and see the effect of that. Sometimes it's in terms of probabilities. Probability densities that we're giving these answers. But you're right that we have a way to incorporate the gluons to also study how the quarks are being formed from that splitting and so on.
Hey, I've read recently that there's a theory that some physical constants, the speed of light and the gravitational acceleration and things like that have some variability over time. They're not exactly constant over time. I'm curious your thoughts.
Okay, that's beyond my field of expertise, I should say. But one thing that we, as scientists, we should be. So the question was whether some physical constants are allowed to change over time, unlike popular belief. So one thing that we should shy away from, scientists, is not to be open-minded and investigate all of these phenomena. There are possibilities that there is physics we don't understand. Even within the visible matter, there are phenomena we don't understand, or else we are using the visible matter to prove that there are things beyond the things that are described by the visible matter, such as the dark matter. So I would say it's open to investigation and further work by experts. So that's interesting to be seen.
At the early slide, you were explaining about a rubber band and marbles.
Yes.
And how you pull them apart. Then you explained that you can actually pull them apart I wasn't sure if, was that similar to cell division? Are you creating new particles when you're doing that, or?
Yes, so all of this, there is no vacuum in space. So we don't live in a vacuum. In everyday life, we can talk about vacuum, but not in the microscopic world. There is always a QCD vacuum, we call it, which basically everything lives in a background, which is the very energetic background that has creation of particles, annihilation of particles, and so on. So what happens is that as you try to pull apart this rubber band, and you're inside this hot vacuum, what happens is that two particles, they couple to this rubber band, they split it into two, and you have now a set of two bands. Yes, so it comes, this energy and these particles, they come from the QCD vacuum. That is very energetic.
Are there any particular or potential applications in unraveling the secrets of the proton that you're excited about?
Okay, yes. But they're extremely technical. How can I say this in a simple way? So, yes, so everything I talked about today, it approaches the particle as if it's, you take a picture of it. Everything I showed is one-dimensional. You see a circle and quarks inside. But there are more interesting questions that are related to assuming now that this is a three-dimensional object and understanding the position of the quarks inside the proton. We call this 3D tomography. That's my current research, and that's what all my students work on, and my funding is dedicated to that. And it's something that the EIC will study. EIC will become operational maybe in the next decade, and our bet is that we will beat them first and have some predictions for them to use.
We have time for a final question.
Confused by one slide. You put up a slide with a proton, and you described discretization of that proton.
Yes.
Then below it, you put integral math, and if you take discrete samples and you integrate them, you get a continuous sample again.
Yes.
So I can't understand why you take discrete samples just to subsequently make them.
Very good point. Okay, it's a bit technical, but maybe not so much. So the question is about this plot I have shown. Oh no. Okay, this plot that I have shown here that says, and if you look at this, it says that I discretize space. So mathematically, this means I have integrals. I turn them into sums. I cut them in pieces and add them together. So this is to perform the simulation. So we do the simulations on a finite lattice, and we have summations. We do not have integrals. We repeat the calculations for several ensembles, minimum 3. And then we take these results and we extrapolate them to 0 lattice spacing. So we take the limit that this pixelization, it becomes so small that it's 0, and that's how you reconstruct a physical quantity. So we don't do it on the computer. We do it after we obtain the results pixelized.
Okay, let's thank Martha again for this.
Thank you.